Statistical models require examples to learn, but in modern datasets, the number of features, dimension n, often vastly exceeds the number of specific training examples, m. The geometry of this problem is absolute. If you have only 2 data points in a 3-dimensional volume, they can only span a 1-dimensional line. The vast majority of the 3D volume surrounding them remains entirely empty. This empty space breaks the standard maximum likelihood estimator. When we use this formula to calculate a covariance matrix, we are attempting to map how the data varies across all available dimensions. Because all the probability mass is flattened onto that lower dimensional line, the data occupies 0 volume in the higher dimensional space. Consequently, the determinant of the resulting covariance matrix collapses to exactly 0. The matrix is singular. In linear algebra, a matrix with a determinant of 0 cannot be inverted. Attempting to compute the inverse term forces a division by 0, which sends the calculation toward infinity. This is a terminal issue for standard Gaussian modeling. The multivariate Gaussian density function relies entirely on this inverse to compute probabilities. Direct maximal likelihood estimation is mathematically non-functional in any high-dimensional, low-sample regime. To model complex datasets without these failures, we must capture feature correlations without relying on the calculation of a full covariance matrix. One logical response to avoid a singular matrix is to artificially restrict the space of parameters the model is allowed to consider. To fit a full, dense covariance matrix, we require a sample size of at least n plus 1. Without that data, we cannot reliably estimate every interaction between features. The diagonal covariance alternative lowers this requirement to just 2 samples. However, this restricts the Gaussian density contours to axes-aligned ellipses. This restriction comes with a heavy trade-off. It forces the model to treat all variables as entirely independent. An even stricter restriction is spherical covariance, where every entry on the diagonal must be exactly equal. This strips away all unique variance per feature, reducing the complex geometry of the data into perfect, rigid spheres. While these restricted matrices avoid the problem of singularity, they sacrifice the model's ability to discover meaningful correlations between variables. Factor analysis provides a different path, using a generative architecture to embed low-dimensional correlations inside high-dimensional spaces. The model assumes that the high-dimensional data we observe actually originates from a lower-dimensional hidden variable, the latent variable. In the first step of this generative process, we sample the latent variable z from a standard normal distribution with an identity covariance. Next, we map this variable into the high-dimensional space using a transformation matrix lambda and shift it by a mean vector. This mapping alone still leaves the data perfectly flat. If we stopped here, we would still be dealing with a singular covariance matrix. To fix this, we inject independent Gaussian noise for each feature. This psi noise pushes the points off the flat plane and into the surrounding volume. This produces the complete generative equation. The observed data x is the result of the latent mapping plus independent noise. By physically constructing a low-dimensional manifold and padding it with noise, factor analysis safely embeds correlation in high-dimensional space without the risk of singularity. To use this model for prediction, we need to determine the exact probability distribution this generative process creates for our observed data. We find this by constructing the joint Gaussian distribution for both the latent variable and the observed data. Because the latent variable and the noise are independent, their expected product is 0. This simplifies the cross-covariance block to just the transformation matrix, lambda transpose. The covariance of the data we actually observe is located in the lower right block of this joint matrix. The resulting marginal covariance takes a specific algebraic form, lambda transpose plus psi. The first term, lambda transpose, is a low-rank matrix. It captures all the structural correlations between our features. The second term, psi, is a diagonal matrix representing the independent noise. It fills in the gaps along the center diagonal. Adding this diagonal noise ensures the combined covariance matrix is full rank and fully invertible. This structure is a mathematical solution to the singularity problem. It decouples the structural correlations from the baseline noise. Directly maximizing the log likelihood of this marginal distribution is analytically impossible, as there is no closed-form solution. Instead, we use the Expectation-Maximization, or EM, algorithm to iteratively fit the parameters to our data. The E step estimates the distribution of the latent variables, while the M step updates the parameters to maximize the expected likelihood. Solving the M step for the transformation matrix involves complex matrix trace derivatives. The final update equation for lambda resembles the normal equations used in standard least squares regression. However, the denominator contains a term that leads to a common implementation error among practitioners, the expectation of the outer product of z. It is a mistake to substitute the squared mean of the latent variable directly into this term. The expectation of an outer product is equal to the product of the means plus the covariance. To be mathematically sound, the update must incorporate the covariance of the posterior distribution, the uncertainty remaining in our latent estimates. The M step must account for this inherent uncertainty about the latent variables, rather than treating our best guess as an absolute truth. A standard dense covariance matrix requires n-squared parameters. Factor analysis replaces this with the compact lambda and diagonal psi matrices. This reduces the parameter count to roughly n times k, where k is the number of latent factors. By lowering the parameter count, we neutralize the n much greater than m problem, allowing us to fit models with much smaller amounts of data. The result is a stable probability boundary that remains robust even in high-dimensional contexts. Factor analysis proves that when data is sparse, projecting a geometric structure into latent space can expose deep correlations that standard statistical models are unable to detect.